Okay, in the last video we learned about delta G, which is Gibbs free energy, and we said that if delta G is negative, it tells us that a reaction is spontaneous. If delta G is positive, it tells us the reaction is not spontaneous. And if delta G is equal to 0, it is at equilibrium, which means there is some sort of connection between delta G and equilibrium, and we need to deal with that. A quick recap. We mostly dealt with, in the equilibrium chapter, we dealt with Kc or Kp, and I kind of briefly mentioned Keq, but I want to recap this real fast. It's essentially like Kc and Kp together. So what that means for us, Kc is everything in terms of concentrations, and Kp is everything in terms of pressures, or in terms of atmospheres, because everything is in pressures of gases. So what this means is it's still an equilibrium constant. So Keq is still an equilibrium constant. It's still products over reactions, just like it was for Kc or Kp. Essentially, all it means is that whenever we see anything that's aqueous, we do it in terms of molarity, just like we did for Kc. And anything that's a gas, we do it in terms of pressure, which would be atmospheres. It's supposed to be an M, sorry. Okay, so it's kind of like both of these together. Not a big deal, and actually it kind of makes things a little easier. So, in the last video, we saw that delta G, if it's equal to 0, means that you are at equilibrium. Well, there's an equation that explains how this works. It turns out that the delta G of that reaction, of whatever reaction it is, at standard conditions, this does not mean that this does not have to be at standard conditions, but this is equal to negative RT times the natural log of Keq. As per usual, natural logs and logs pop up all over the place. So a couple things about this. This R value, since things are in terms of energy, we are actually going to use that 8.314 joules per mole Kelvin value that we used at the beginning of the semester. And the temperature just has to be in Kelvin. Otherwise, the units won't cancel. But, yeah. So in the previous problem, we solved for a delta G value at standard conditions. We looked up the values for the delta S, and the delta H was given. And so we want to know, let's just try it. We want to know what is Keq for the previous problem. So it's not in this video, but obviously you have access to the previous video. So in that equation, or in that problem, we solved for delta G at standard conditions, and it came out to be negative 76.0 kilojoules per mole. Okay. And let's just solve for Keq at room temperature, 298 Kelvin. So delta G at standard conditions equals negative RT over natural log of Keq. We are trying to solve for Keq, so I'm going to divide negative RT off of both sides. And that leaves us with natural log of Keq equals all this stuff. I guess I'm going to rewrite this over here. Natural log of Keq equals delta G. I'm just going to put the negative on top. It doesn't really matter. Divided by RT. To get rid of natural log, you guys, we during the acid-base chapter, we used regular log, but now we're going back to natural log. Natural log is e to the x is the inverse of that. So to get rid of natural log, we do e to the x on both sides. So Keq is equal to the negative delta G, e to the negative delta G over RT. Well, we have all of those values. This value is 76.0 kilojoules per mole, but this value is in joules per mole. So something's got to give. We either need to make this kilojoules or make this joules. I'm going to choose to make this joules, so we're going to multiply this by 1,000. So our answer is going to be e to the, it'll be negative times negative, so it'll be positive 76,000 joules per mole divided by R, which is 8.314 joules per mole Kelvin, and times 298 Kelvin, and all of this is an exponent of that. So this comes out to a very big number, and we get e to the 30.7. When we type that in, this is what KEQ equals. KEQ comes out to 2.15 times 10 to the positive 13th. So we said for that previous reaction that a negative delta G means it's spontaneous, and negative 76 is a pretty reasonably large number, I guess. We don't have a whole lot of point of reference for this, but it makes sense that when you get an equilibrium constant, we said that if the equilibrium constant is equal to 1, that the amount of reactants and products are pretty much similar, and the forward reaction and the reverse reaction are pretty much equivalent. This is 10 to the positive 13th. This means that it is primarily going towards products. It is very much so going in the forward direction. So these two numbers agree. If this is negative, it's spontaneous. If this is above, the bigger the number this is, the more spontaneous in the forward direction it is. So it all kind of agrees. It's all kind of one concept. Okay? So, not too bad, right? Not drastically different than anything else we've done. Okay, we just got a new equation. Okay, but now we know that delta G and KEQ are related. Okay, they're all kind of one concept. So even though we didn't have this reaction at equilibrium, we can solve for what the KEQ would be at equilibrium at any given temperature. Okay, because it's based off the standard conditions. All right, thanks.